Okay, let's get started. So if you have a quiz, God, what number is it? 17? So 17, you put it there. If you have a homework 6, also turn it in. If you, so per my announcement, because of what President Casey said, if you need some extra time to complete your homework 6, you are free to do so for the rest of today and turn it in by email or to my mailbox, whichever you prefer. Any questions before we start? Yeah.
So do you know how you're going to handle online classes?
I do.
I feel like you're pretty well set up for it.
Yeah.
Like you have all your stuff recorded from previous semesters.
Would you like to know how I would plan to do it?
Just make us watch some videos.
Yeah, so what I want to do, so this is such a small class that we could basically do anything we want. So it's not like it's my decision and you have to accept it. It's just, let's do something that makes sense. So I could just make lecture videos and make you guys watch them, or I could set up a Google Hangouts or a Zoom meeting, and I could do a lecture and we can do a discussion at the same time. And so there are a lot of different things that we could do. I could just make PDFs of lectures and not even have a video. Whichever you guys prefer. We don't have to decide now. We can wait until at the end of spring break week. So, but I do have some options to do here. When's the test day? Exam 2? So I think it's not the week after spring break, it's the one after. So if it remains impossible to do an exam 2 in class, what I want to do is instead of having a test, I'll have you guys do a project instead on the material that would have been tested to show that you understand the material. Because, I mean, I can't have a test in here if they don't let me. So, yeah. Any other questions? Okay, so what were we talking about last time? Yeah, DPDAs, right? So I think this is the only 4-letter acronym we'll see. Yeah, and actually after spring break we'll get to a 2-letter acronym, so everything balances, right? So what does a DPDA stand for? Right, so a deterministic PDA. So that means that there's exactly one choice of transition to do at each point. So it's not like the PDA can get stuck. It's not like we have 2 different choices. We have exactly one choice. So I asked this question. Was anyone able to figure out a DPDA for it? So let's look at the PDA we actually did make for 0 to the n, 1 to the n. So I'm just going to copy it here. You don't have to copy this down because I'm going to make another machine after this. Okay, so this is the machine if I didn't make a mistake. This is the PDA that we made before for 0 to the n, 1 to the n. So is it the case that no matter which state that you look at, there's exactly one transition you could ever do for a given symbol to read and a given symbol on the top of the stack? Is there ever any choice where we have two different transitions we can do? Yeah, which one is it in this case?
It's the self loop with the 0, epsilon 0, and then the triple epsilon.
Right. So if I have a 0 on the input, I could either do that self loop or come down to Q2. So this is not a DPDA. But what was the reason I mentioned when we did this of having that triple epsilon transition in there? What was the purpose of doing that? Well, I'll actually refresh your memory. It's because we want to accept the empty string. So if I have that downward transition be like 1, 0 going to empty, well then there's no way to get to a final state at that point because I have to read something. So is there a way we can modify it so it is deterministic? And it turns out yes. So I'm going to rename the states to be R0. So the first transition is exactly the same, except R0 is a final state because we want to accept the empty string. And then we have a state R1. The self loop is exactly the same. The downward transition is 1, 0 goes to empty. And then R2 is again the same as before. And then finally, the last transition is the same as before. Okay. Is this a DPDA? So at each state, do I have exactly one transition to apply at every point? Well, let's look at the first one. Do I have exactly one transition I could ever do? Yep. Well, there's only one, and no matter what the input in the stack are, I can always do it. So that's good. For R1, no matter what the contents of the stack are and the input, could we take exactly one transition? Well, what if 1 is on the input and $signs on the stack? Which could be very possible, because I could feed a string of all 1s to this machine. So the first character is a 1, but the top of the the top of the stack is a $sign because of that first transition. So what could we do then? Well, what would it mean if a 1's on the input and a $sign's on the top of the stack? What would that indicate?
Couldn't we make another transition similar to the 1, 0 epsilon, just $sign epsilon?
Yeah, but let's think about what that means. Yeah.
It's an empty string.
What's that?
It's an empty string.
But we've already accepted the empty string. So I'm asking, like, is there a way to, what would it mean if I have a 1 on the input and a $sign at the top?
That means we have no zeros.
We have no zeros, but what does it also mean? It doesn't belong. Right. So we should never accept it. So what I would recommend here is to have a transition from R1 on $sign goes to, it doesn't really matter what we push. And then I'm going to have a state here called reject. Okay. What about, well, 0 with a $sign on the top is fine because we could take that self loop there. If a 0's on the top and I have a 0 on the input, I can still take the self loop. So this really is the only case that we haven't considered. What about state R2? Well, let's see. If I have a 1 on the input with a $sign on the top of the stack, is there exactly one transition I can do? Yeah, namely the one that goes to R3. I can't do the one that, on R2, but if I have 1 on the input and $sign on the stack, I have one transition left. So I can take it because I'm not reading anything. So that's fine. What if I have a 0 on the input and a 0 on top of the stack? From R2, I mean.
That should also go to reject.
That should also go to reject, right? So I'm doing this purely as to show you that we need to incorporate other transitions. So in principle, could we go through every single one of these states and figure out what's missing? Yeah, so like there are things from R3 that are missing that should go to reject. So to make this a lot easier for ourselves, do you think we should consider all of these cases that don't work? Or is there a way that we can handle this? Here's what you can say. So all unwritten transitions go to reject. Can't spell reject to save myself. The reject state. And because reject is also a state, we should have self loops on them for all of the combinations also. For combination. And actually what those are going to be 0, epsilon, epsilon, 1, epsilon, epsilon. Because I need to have transitions in there, and I can't assume that there's anything on the stack at this point. So, yeah. So what I'm saying here is that because there's not anything on the stack and the reject state needs transitions for each of the combinations, we need to have these transitions in there that don't pop anything, but we have one for the 0 and one for the 1. Okay? Any questions about that? Yeah.
Do you have to have the reject state, or can you just fix it where it doesn't belong in the language? Can you just like get stuck in some state?
We could with a PDA, but this is a deterministic machine. So we must have exactly one choice of transit. So it's kind of like a DFA. At each state, you always will have a transition to do. It's the same kind of idea here. At every state, you will always have one transition to do. Other questions? Okay, so why are we even talking about deterministic machines in the first place? Well, we talked about the result of context-free languages and complement last time. So we talked about CFLs and complement last time. And what did we show about the context-free languages and complement? Yeah, so it's not closed under the complement operation. So there is a CFL, I'll call it L, such that L bar, the complement of L, is not a CFL. And that's what we showed last time. Okay, so what do you think the purpose of making a deterministic machine is for our purposes?
Well, we couldn't do just the complement of a PDA, but with a deterministic one, we can just do what we did for like NFAs or DFAs, where we flip the accept or not accepting.
Right, so if we can flip which states are accepting and not, that would show that the what are called deterministic context-free languages are closed under complement. So what I'm going to define here is a DCFL is a language, or the set of languages, I guess, corresponding to a DPDA. Okay, so the question we would want to ask now is kind of like the one we did with NFAs and DFAs. We said, well, we have NFAs which have this non-deterministic capability. Are they the same as DFAs? And we showed that they were. We can always convert an NFA into a DFA. So then a question you may want to ask here is, are the CFLs and DCFLs the same? So the same kind of idea between deterministic PDAs and just normal PDAs. So the question we want to ask and answer is, are the DCFLs and CFLs the same? And this is actually of importance in compiler design, because a non-deterministic machine we can never actually implement in practice. But a deterministic PDA, we can definitely do that for sure, because it's deterministic. And if they are the same, then great. Then any PDA that we are interested in, we can convert it to a deterministic PDA. If they're not the same, well, that's kind of sad, because then there must be some problems that a DPDA cannot solve, that a PDA can. Okay? So what we're going to show here is that DCFLs are closed under, wait for it, complement. Dun, dun, dun. Okay. Okay. So the idea, which seems reasonable at first, but it actually has some subtle technical problems, is let's just flip the final and non-final states. Okay, that seems reasonable. So, so I'm going to put this in red because it's an idea that does not work, but it's just a reasonable start to it. So idea is flip the final and non-final states. Seems reasonable. Why does this idea not work? And in fact, we don't even have to look far. Let's look into the DPDA we made on the right. Yeah.
Because when you flip it, what do you call it? You begin with the pop.
No, the transitions don't change. It's just the states that are changing. Well, look at this the DPDA we just made. Suppose that the two states on the left are no longer final, and then the two states on the right are final. So we're flipping which ones are final and non-final. Do we get the complement? No, why? Exactly. So we can still get the empty string. Here we get the empty string because we can just stay in the start state. But if we flip the final and non-final states, we could take the transition over to Q1 and still get it. So it's not enough to just say flip the final and non-final states. So it's the same problem that we had with PDAs where we couldn't just flip them. So this idea doesn't work. So let's think of a better idea. Well, why did DFAs allow for the capability of flipping final and non-final states? What allowed it to do that?
Well, for one thing, there wasn't any epsilon transition.
Well, there were no epsilon transitions. So every transition reads something. Fair enough. Well, DPDAs don't have to read anything, so that's not enough to get what we need here. What is something that could happen with a PDA or DPDA for that matter that a DFA cannot do? What is the criteria for accepting a string in any machine?
We have to read the entire input.
You have to read the entire input. Can DFAs fail to read the entire input? No, they can't, because there's always a transition that reads. right? So at any state that we are, we'll always consume another character. What about for DPDAs? That's not true. So here's what we would want to do. We want to ensure the DPDA always reads the whole input string, regardless of what happens. So if it reads the whole thing, then we definitely have made progress here. Okay. Well, what else could happen? So what if we have something like this? So if I have a state here, goes to another state, and the first one, it doesn't matter which one it is, but one of them is final, the other one isn't, and we have an epsilon transition. And it doesn't matter what we pop or push here, but it has an epsilon transition here. Is this going to cause a problem for us? Yeah. So what do we want to do? We want to modify the transitions so that if we are in a final state, sorry for all the text in this one. If we're in a final state and take epsilon transitions, we stay in a final state. Okay, so if we are somehow in a final state and just do epsilon transitions only, we should stay in a final state. Because if we have this behavior where we have the ability to go out to a non-final state, then when I do the flip operation, then this new state is going to be the final one and we'll still accept the string because it's consisting only of epsilon transitions. So it's the same problem we had before. Yeah.
So for the example that we were using beforehand, how we got rid of the epsilon, like the triple epsilon, would we do something similar where we take like the first transition where we read a 0 and then get rid of that epsilon transition?
It's actually much more systematic than that, but it's so in the example that we had here, we had to rely on the fact that the reason that triple epsilon was there was so that we can accept the empty string. Then we had to modify the rest of the machine. Here we got to make it more systematic so that we don't have to look at the entire structure of the PDA. We can make little tiny adjustments and not have to worry about understanding what the PDA actually does first. Any other questions? So let's see. So how do we accomplish the first one? So I'm going to call the first one 1 and the second one 2 so that I can refer to them down here and we know what's going on. So let's do the first one. So we want to make sure that the PDA will read the entire input string. Okay. Well, what are the possible things that could happen that will cause us to fail to read the input string? So it turns out that there are 2 ways. One way is it tries to pop an empty stack. Okay, it could pop an empty stack because if I have a state right here where every single transition involves going out of it involves popping, and I have an empty stack at that point, we're stuck, right? So what could we do to mitigate this? To avoid popping an empty stack? Well, what was the trick that we used in other PDAs so that we never hit an empty stack and caused a pop to happen? What did we do? We had a $sign on the bottom. Old tricks being used for new problems. So how are we going to handle this here? So this is exactly what we're going to do. So here's the DPDA. Here's the start state. So for our convenience, I'm going to have one state in here. I'm going to call NF, which means it is not final. And I'm going to have some other state that is final right now. It's final right now. Because there will be different behavior for what happens. Okay? Well, let's see. What could we do? Well, at the beginning, I don't know what the start state does. But how do we enforce that the stack has a $sign on it at the very beginning?
We added an extra transition that just pushes the $sign.
Exactly. So I'm going to make a brand new state, Q0, that is going to have exactly one transition, which is putting the $sign on the stack. And of course, $sign is not a stack symbol used already. It's just a brand new symbol. Cool. Okay, well, what could we do here? So let's see. So what if we have a transition that that is like this? So we have epsilon A goes to epsilon in the DPDA part.
Are you asking like what the behavior should be like
Yeah.
in that state?
Yeah, so let's actually try to think about this. So we want to allow for, so the things that could be on the stack at this point are any stack symbol or the $sign. So if it's any other symbol, we want the DPDA to do exactly what it would have done before. But if it's a $sign on the stack, what should we do at this point? Well, it could be that there's some other transition that has no pops on it, right? So if there's a transition that has no pops at all, should we have any behavior with the $sign on this, with this state? Well, let's see. So suppose that NF has a transition that does not pop anything. Do we care about the stack popping an empty stack here? No. So if we have any transition that, yeah, go ahead.
How is that deterministic?
It's not. Yeah, that was my mistake. Yeah, I'm actually going to modify this. So let's say that it's reading an A, but that is not important. I'm just saying, is there a transition that does not pop anything? And in this case, there is, so we're not going to do anything. So suppose that there is some other state, I'm going to call NF2, where there is no such transition. So NF2 has no transitions that do not pop. So I'm supposing right now that NF2 has transitions. Every single transition it involves in pops something. Every single one. So what should we do if we see a $sign at this point? Well, let's see. We're in a non-final state now. So that means that if I didn't do anything, we're going to get stuck in this state because the stack has a $sign on the top of it, and every transition pops the stack. So that means it was trying to pop the empty stack before. So for that reason, should we ever accept the string if it's in this case? No. So what we can do is something like the reject state that we had before. So what I'm going to do here is I'm going to have a transition here that is epsilon $. Let's see if I have my notes right. Yeah. $, goes to empty. And then it goes to a reject state. Well, we still have more work to do with the reject state because we want the entire input to be accepted. So what should we do to the reject state to make sure every input is accepted? Well, what did we do? Go ahead.
For the other reject state we just read the character 0 or 1 and just had epsilon.
Yeah, exactly. So what I'm going to do here is I'm going to have a transition of the form A epsilon goes to epsilon for all A in sigma, which is the input alphabet. And that state is deterministic because for every choice of input and pop symbol, I have exactly one of those 4 choices here. So it is deterministic. It's just like a DFA where we have a dead state where we just read all the rest of the input. It's the same idea here. And we can't assume anything that's on the stack, so there's no point in doing anything with the stack here. Any questions about that? Okay, what if we were in the final state with the same idea?
I feel like that's, if we're in the final state, are you saying that the last thing we have is the $?
Yeah.
I feel like that's a good.
Right. Then that means we should always accept that string, right? So we should do something similar. Except, in this case, we should go to a state where we always will accept the string, but we still have to read it all. So let's do something similar. And I'm going to call this the accept state. Oh boy, we might not have enough time to do all of it. We'll see. Let's see what we can do. Any questions about this? So we're enforcing that the DPDA will always read the entire input string. Okay, so the problem that remains now is we still have that issue of epsilon transitions going from a final state to a non-final one, or vice versa. So how do we handle that one, which is the second criteria? So what we're going to do here, and I don't know how they came up with this. Go ahead.
So you said there are 2 ways to fail reading the entire input, and one is always popping in empty stack.
Oh, I need to remember what I was saying. Yeah, the other one is it didn't read all the input. And I didn't do this on the accept state. So here on the accept state, I'm going to do the exact same thing as we did with the reject state to make sure that the input is always read. Yeah, thanks for reminding me. Okay. Yeah, so the 2 cases are it pops an empty stack or it doesn't read the entire input. Okay. So let's see. So what can we do here? As I was saying, I'm not sure how they came up with this, but it's a pretty slick way of enforcing that whenever you are in a final state and have only epsilon transitions, you stay in a final state. So one thing to keep in mind is, could it be possible that I have a state here, maybe has outgoing transitions, but no incoming transitions? Is that possible? Am I allowed to do that, is what I'm saying. Yeah. So That's actually one of the things that we're going to exploit in some sense. So I'm going to describe what the method is, and we can just bask in its brilliance because it is truly slick how it works. The first step is we're going to make a copy of each state, and the copy is always final, a final state. So, like if I have a state Q here, I'm going to have a Q sub F corresponding to it. So, if I had another state R, which was final, then I'm going to have an R sub F state, which is also final. Okay, so I'm just going to blindly make a copy of every single state. The copy is always final. Fair enough? Okay, so what should we do? Well, should we ever have the possibility of an epsilon transition going from a non-final state to a final state? Or the other way around? No, we should not allow for that possibility. So if Q going to state R, maybe I should give it a different name because the R state over there is final. I'm going to call it S. So if I have a transition from Q to S, both of them non-final, which is epsilon, and then it doesn't matter what we pop or push there. So if that is a transition, then we add Q sub F going to S sub F with the exact same transition. Okay? So you can think of like the F states as being, we're in the final states now, and we're going to only escape the final states if we are going to read something. So if I have a transition that does not read anything like these ones, then I'm either going to stay in the non-accept states or stay in the final states. So that kind of avoids the problem. But so suppose that we have a different situation where we have Q going to state R now, which is the final state, which is an epsilon transition. Which is obviously a problem because if we want to complement now, this is an issue. What could we do? We're going to redirect this could we have that? Interesting. I don't have that in my notes. I thought that would be a... Okay. I have the order wrong. So let's just say that we have the state R going to state Q. Yeah, okay, this makes sense. So then now, because of that, we're going to redirect this transition to Q sub F. So the way to picture this is we have state R here, Q here, R sub F down here, Q sub F over here. So normally we would have had a transition that went to Q, but now we're redirecting it down to the F states down here. Okay? So then so these handle the transitions that don't read anything. What about the states that do read something? So then if we have a transition like Q goes to, I'll keep it with S. Do I have that right? Yeah. So if Q goes to S is a transition where it does read something. So we're reading an A on this transition. Then we're going to do the following. So we're going to draw our picture just like before with Q and S and the final versions below it. So if we were in the non-final version, or it may not be non-final, but if we were in the original states here, I want to do exactly what it would have done before. Because if it's a transition that reads something, I don't care if, we don't have to worry about flipping the final and non-final states here. So what I want to do is, I'm going to do exactly what it would have done. But if we were in the final version of Q, well, I want to go back to what the original machine would have done because this is a transition that reads now. So if I have a transition that reads and I flip the final and non-final, well, it doesn't matter because I'm reading something. So here, I'm going to have Q sub F go back up to the top row instead of just go horizontally to S sub F, I want it to go back up to state S. So now, let's just bask in how someone could have possibly come up with that. So I'm not going to verify it here. You could verify that this is in fact a DPDA. So this really is a DPDA. So that's good, but there's still one more thing that we need to do. Suppose that, so another thing about DFAs, we always will read the input string, right? But could it be possible in a DPDA that we are in a state right now and we're going to take a bunch of epsilon transitions back to the same state and not change the stack contents at that point? So like if we're in some state right now, we're going to take a bunch of transitions. Let's just say X is at the top of the stack, and we go around and come back, and there's still an X on the top of the stack. I haven't read anything. Is that possible? It turns out it is. So let's see. So what I'm going to do, oh God, now we have like no time. So what I'm going to say here is that we have to remove what are called looping situations. I'm not going to go into the details of what this is, but a looping situation is Q with X. So Q is a state, and X is a stack character, where if we started in Q with X on top. Nothing is ever popped below X, and no input is read. So it turns out that you can actually look into the PDA and make and figure out whether a state with a stack character is a looping situation. I'm not going to go into it. It's not important for this. So the final thing we need to do is, well, we need to find out here which, so I promise this is the last step, which states are reading states. So then this means that we have a state here that reads something. And then I don't care what it pushes or pops. So if this state actually reads something going to some other state, and every single transition coming out of it is of that form, then it's a reading state. So what could happen? Well, let's see. So then, sorry. It's a reading state if, sorry, I'm getting my details mixed up. So if we read an A and no pop, Q is a reading state. So the sole purpose of Q here is just to read. It doesn't do anything with the stack in terms of popping off the stack. Well, the thing that could happen is we could have a transition that looks like this, that does both a pop, actually it doesn't really matter, but it does both a read and a pop. So Q is not a reading state now because it has a transition that reads something and pops something. So purely for the sake of time, what you do is you transform this into two transitions. So the first one, we don't read, then do the pop. And on the second one, we do the read, no pop, and whatever would have done with the push here. And because of that, we're going to call QX a reading state. And if Q was a final state, QX is also a final state, because we don't want to have a final state going to a non-final state. And then now, after all that, invert which states of the reading ones are final. Okay. Any questions about that long series? So the key here is to understand that DCFLs are closed-ended complement, CFLs are not. Are DCFLs and CFLs the same? No, because one's closed-ended or something, the other one isn't. So have a great break. I'll see you after the break.